Okay, we'll start with the top part of that slide first. And let me get into an explanation of RMS, or root mean squared. So you'll notice that as you go across the slide, you start with DC current. So DC current, like in a battery, it's steady, the voltage is steady, and the area underneath over time should represent the power associated with that particular output of current. So if I can do my little pointer. So I've purposely chosen the voltage here at 70.7 volts because the equivalent AC is going to come up to a peak of 100 volts. Now AC stands for, of course, alternating current, and the waveform is considered a sinusoidal waveform, or sine for short, because that's the mathematical function that's associated with that wave type. Okay, now where we get the RMS in is that if we were to take a number of little samples, just think of a number of little vertical lines going up and down, right up to the tip, and then down again, and the more samples you have, the better. Then with each sample, you'll register a voltage. This one here would be very low, this one would be 100 volts, and that's an instantaneous value, not an RMS or a peak value. That's an instantaneous measurement that's made. And then you square that value. So up here it would be 100 squared, or 100 times 100. What's that, 10,000? That's the value you would get there. But all of these would be, of course, much less. You would square that value. So you've got the RMS, you've got the square part, the S part of it in place now. So you square the value you take, then you average the value over all of the samples you've taken. That's the mean part. So if you've taken 1,000 samples, you've sampled 1,000 times up here and down this wave, that's the mean or the average, the number of samples you've taken. You divide that, of course, into the squared values, and then you take the root, the square root of that. So you got that collection of values, you take the square root of it, and you'll come out with the RMS value. Now you say, why in the heck did they do that? That's pretty complicated. It's almost like taking one step forward and one step back. You know, you're taking the square of a value, then you're going back eventually and taking the square root of what you've collected. Well, what would be the alternative? So you think of, well, listen, don't they have arithmetical means? Like, say you have a classroom of 30 students, and maybe it's grade 8, and of the 30 students, you know that they're probably all falling within a particular weight category. Some might be somewhere between 4 and 5 feet, but you'd probably have almost no possibilities of a grade 8 student being over 6 feet tall, nor would you have a grade 8 student usually being under 4 feet tall. So you know it falls within a particular narrow band of weights. But then you go ahead and you weigh all the students, the 30 students, and you add up all of their weights. Then you divide by the number of samples you've taken, the number of students, and you come out to the arithmetical mean. That's the most common average or mean type of measurement that's taken. So you might say, well, okay, fine. Why didn't they do that here? Well, the reason is, and it comes down to mathematical requirements and statistics. And the reason is that when you're dealing with a classroom full of kids, you know, you're dealing with a pretty sporadic population of a limited number. And so you have a certain category, and you can very easily take an average or a mean of that particular category because there are limits or boundaries associated with it. Now, that wouldn't always work for everything, would you? Because let's say, to give you an example, you have a Gaussian distribution. Now you know the familiar bell curve where you take a population and now you have a much more diverse population of samples. However, if you place them all in a particular category, say of weights over 100,000 of the population, you'll have this bell curve. And the top portion of the curve and the sides up to a particular average on either side represents the majority of the population. But on the outliers, you have people who are very, very tiny, and you have other people who are very, very tall. Now, if you simply take the arithmetical mean of that and you put a slice right across that average, what does it do? Well, it gives you an arithmetical mean, but it doesn't tell you much about all of those outliers, does it? In fact, it's completely misleading. So when they came to RMS, they had to arrive at an average that would represent the particular type of population we're dealing with. It's a wave that travels in time, and yet it's a periodic and predictable wave that functions like it does. Once you've got a given voltage, that's the wave you're going to get time and time again. So as you progress time-wise, you have to have a way of arriving at an average. And so mathematically, the root mean square answers that particular requirement. It's not the only average or mean, because there's all sorts of different averages and means. But just to let you know, that's a little bit about the background. We can't get into all the mathematics associated with it because that's probably not of a great deal of interest to you. But there's also a physical requirement for this particular wave. If you take a resistor and you stick it into a beaker of water and you pump current into that resistor, the resistor heats up and it starts to heat up the water. So you can actually measure the transfer of heat into the water by measuring the temperature of the water, right? Now if you put a battery on that and of a particular voltage and current, and you can drive a electric current into the resistor and heat up the water to a certain measure of temperature. Now if you take an AC source, like from a generator or even from an output plug, you'll arrive at, by a little bit of trial and error, that you can get the same heating or power transfer effect from a certain amount of AC voltage as you can with the DC. It arrives at that the same amount of power, as Radar said in his answer to the question, is 70.7, or RMS. The RMS value of the power of AC is equivalent to the DC current and voltage of that particular level. So 70.7 volts DC at that particular current is going to be equal to 70.7 volts on the AC waveform, right there. And it sort of makes sense, doesn't it? Because, you know, there's all this spare space here around the waveform, and of course it goes negative. There's that spare space, and so on. And if you kind of lumped it in all together, you'd probably have something like the area underneath that DC portion. So that's the story behind RMS. And of course there are other measurements. There's peak voltage here that goes from a high positive or a low negative to the 0 volt line. You have a peak to peak voltage, which goes from the tip of one waveform to the tip of the lower waveform. There's also an average voltage as well, but we won't get into that because it has to do with rectified DC voltage, and you don't need to know. It's 0.637, but you don't need to worry too much about that. Now, I've taken a half-wave rectifier over here, like a 35W4, for example, and when you put this AC waveform into it with the current, it rectifies it. It allows current to flow only in one direction, from negative to positive, and what you get out is a half cycle of this AC waveform, and it cuts off this portion. Now you go into the filter, and the filter will charge up after 2 or 3 cycles, and then it will start to discharge as it carries over to the next cycle. This portion here is missing here. In a full wave rectifier, this portion would be captured and be put into there. But the benefit of the capacitor on a rectified waveform, of course, is that it charges up and allows you to carry over the amount of current, and not quite the full amount of voltage, because this is a ripple faction here, to generate DC in an AC-driven circuit. Okay, so we'll get back to power. And here we got power expressed with a DC circuit as volts times amps. Typically that's watts. But when you look at a radio, and you might look at the label on the back or on the chassis, you'll see something like voltamps, and you'll say, is that the same as watts? Well, basically it is, because the power in an AC circuit is equal to volts RMS times amps RMS. So both voltage and amps are measured in terms of RMS values. And therefore, because this amount of power is equal to this amount of power, DC to AC, voltamps is essentially equal to watts in a DC circuit. So one other thing I might mention that's important, and I just overlooked it, is that because this waveform is more than 70.7 volts, in fact it peaks at 100, you go over to here and you're wondering, say with a given input voltage that you're not quite sure of, how much voltage are you going to get out of the rectifier? Well, you're going to get out 1.41 times the RMS value. So in this case, if you had an AC waveform or AC value of 70.7, well, let me deal with the 100. You'd get out 140 volts. With the 70.7, you'd get out 100 volts. So if you follow that, the output of your DC rectifier is equal to 1.41 RMS. All right, so there's a lot of stuff in there, and I hope I didn't inundate anybody, but let's go down to the second part of the slide. Here's what you need to take away. If you don't remember any of all of that stuff about averages and means and all the rest of it, take away these things. Number one, most meters measure RMS values in true RMS. What's true RMS? Well, say you don't have a sinusoidal waveform. Say you have a complex waveform. Like, for example, in an audio voltmeter, you have a complicated waveform. Or say you have some kind of circuit where there's a triangular or a square waveform, or some other non-sinusoidal waveform. There's a different way of calculating the averages for those, and certain meters will do it for you, will automatically set up the circuit so that it calculates the output in true RMS. So it'll give you the equivalent RMS voltage in terms of that particular waveform. So that's why true RMS measurements are sometimes important. But ordinarily when you take your meter and you're measuring it, now you're usually dealing with a sinusoidal waveform. You know, you're checking your power waveform. You're checking maybe 60 hertz in a circuit or whatever. So true RMS isn't really needed for those type of measurements. But sometimes they are, and sometimes then you have to have a specialized meter. You pay more for them, but it'll give you the true RMS value. Anyway, point number two, the AC RMS volts amps is equal to the same power as DC watts. We've covered this in the discussion. So essentially, all it's saying is what we said up there, that the equivalent amount of DC power is equal to 0.707, or the RMS value of the AC power. They're equivalent. And that's why that measurement of RMS is so important, because you have a way of comparing AC to DC power equivalents. And finally, the third point, not finally, but the second last, is AC RMS volts is equal to 0.007 times the peak volts. So when you're looking at an RMS value of 120 volts, and you plug in your leads into an outlet, a power outlet, realize that the 120 volts is an RMS value, and the peak voltage of that circuit is higher. And it's going to be upwards, 160 volts or so? So watch out, because that's why it bites, as radar says. The last point, I'm sorry, we're at the last point. So rectified AC volts is equal to 1.41 times the RMS volts in. Why do you need to know that? Well, because all of us deal with rectifiers when we're in radio work, and we must know that when you put an RMS voltage through to a power supply and there's a rectifier there, you're going to get 1.41 times the RMS voltage in coming out of that circuit. And you get a pulsating DC that is 1.41 times the RMS voltage in. Okay, so those are the things you need to know and remember. You don't need to get overly complicated, but everybody here that's doing any kind of radio work needs to know those things. So we'll go on to the second slide then, please. First, this is my power add-on, or power up box, and I'm showing you what I have. Then we go back to the plug, to the receptacle. Of course, we'd have a plug that fits into this. And you'll note that on every power outlet, there's a small or a short rectangular connector or connection, plug-in part, and a longer one. And then you've got the rounded one. So the rounded one is ground, and usually there's a green wire coming off of that. The gold-colored pin inside, or connector inside, is the hot pin. It's usually used for the hot pin. There's a longer rectangular one that's the silver pin, and that connects to this neutral. Now, okay, so we get into our outlet, and we say, fine, that's good. So we plug in our power outlet box, power up box, and realizing there's 120 volts from the hot pin to the neutral pin. We come in here and we put in a fuse and a switch. Now the fuse, how do you rate a fuse? Well, are you dealing with RMS values when it comes to rating the fuse? Actually, you're not. And the reason you're not is because of the way a fuse acts. How does a fuse act? Does it sense voltage, or what does it do when it blows?
Time over current trick. Time over current.
Yeah, it melts. The fuse melts. And when it melts, it's only associated with current and with not an RMS value as such, because it's just simply melting because of the heating power associated with a particular current that goes along there. So I've got it here rated at 1.5 times the current. Well, the current, yes, the current is an RMS value, but the reason why it's 1.5 is you give it a little bit of extra allowance just to be on the safe side. A transient might come along in the line, a little bit of a surge. You don't want the fuse popping with every turn of the electrical situation. Let's accept, first of all, that we've got our power-up box just as it's laid out here. And you go into a variac. Now, so radar covered the area of variacs pretty well. And in my particular case, I have an ammeter here, an AC ammeter on the sliding arm of the variac. And then that feeds an isolation transformer. And an isolation transformer is just simply a one-to-one transformer that allows you to put up to 120 volts in and get 120 volts out on the secondary. We'll discuss what the purposes of that are in a moment. But the other thing I might mention is that I put in an outlet that is a 115 volt outlet, like one of these sockets here, on this side and one on this side. Now I could have also put in a switch here so that I could just have the variac operating an outlet all by itself if I wanted to switch out the isolation transformer. Probably that would be a little better. Anyway, there it is. So what do we do? Okay, now if we could pull up the slide, let's get into an application here of the power-up box. All right. Okay, let's go to the power box procedure. So I've written it out as a number of steps that you need to take. And this is to be ultra safe and to do things what I think probably is the best way. So number one, when you go to use this, measure 120 volts AC from the receptacle, the hot to the neutral. Why? Because sometimes the receptacle is wired backwards. And especially in older homes, but it could be also in newer ones where electrical contractors come in, they're in a rush, have to finish the job as quickly as possible, make their money and go. Now usually these days they go around with a ground fault indicator socket and they plug it in to make sure that all the receptacles, the power box, or pardon me, the outlets, power outlets are all wired correctly. But sometimes something slips through and maybe the hot and the neutral are wired backwards or incorrectly. And so if you do that measure, it will tell you right away if a receptacle is miswired, and you want to change that out. So you open up that box, you turn off your power, of course, with a circuit breaker back at your circuit breaker box for the house, and you wire it correctly, remembering that the gold pin or gold contact is for the hot and the silver is for the neutral side. Now, usually the hot is a black wire and the neutral is a white wire, as opposed to the green wire for the ground that goes to the water pipe ground system. Okay, you want to do that first because you want to make sure that everything is wired correctly. In fact, when I was setting up, and I have my little workshop at home, and I noticed that sometimes I was getting an offset voltage between the grounds of some instruments that were plugged in on some receptacles as opposed to other instruments. And we'll get to that because number 2 says measure 2 volts AC or less from the neutral to the ground. If you get more than that, there could be a miswire on the receptacle or somewhere in the power line feeding to it. Why would you even get 2 volts between the neutral and the ground? How could that happen?
I squared R. Resistance in the
One
neutral.
circuit's coming through the ground and one's coming through a conductor.
Ground loop.
Okay, well, I was going to say ground loop like there's an inductive pickup. No, just think of, you have these parallel power lines going all the way all the way through the house, and the neutral and the hot wire and the ground are all running together. They're all parallel together. So there's going to be some inductive coupling between those wires, especially even between the neutral and the ground, and you might get a little bit of stray or residual voltage on those lines. There's not much you can do about that. That's just the way things are. And if you have 2 volts or less, you're probably going to be okay, so don't worry about it. But if it's more than that, you better start debugging your power lines.
See, the neutral, the other thing about neutral carries current. The ground is not a current carrying conductor. So if you have a long run of white, there's a load at the end. Depending on where you measure ground to neutral, you will get some I squared R losses.
Okay.
Get the volts.
Okay, that makes sense too. Okay, number 3, measure all connected instruments. All right, so you got your setup, you got your radio out there, and you plug them all in, and before you turn anything on, just measure the grounds between your box, between the power receptacle, the ground on it, and the ground in your radio, and the ground in the radio to instruments that you're connecting up to it, like your oscilloscope, your generator, and whatever instrumentation you have. And you should be measuring almost 0 volts between all of those grounds. If you're not, you've got some stray voltage or leakage around somewhere, and you've got to debug that. You've got to make sure you don't have that. Otherwise, when you turn on your scope, you're going to have a 60 hertz waveform with your tiny little signal being carried on the back of this huge 60 hertz waveform showing up on your scope. And that's an annoyance, and you don't want that. And that just complicates the measurements that you want to take. So you got to get rid of it. All right, so that's why that's there. Now, point 4, plug AC/DC radios into the ISO. I put /variable socket. I had to squeeze that in. I realized, I should have put both of them in. Okay, and with hot to hot. Well, so by that I mean go back and check, especially if you're dealing with an AC/DC radio, which has a floating ground. And there it is. So here's your radio. That's the cabinet, and that's the chassis, and it's in usually some kind of a plastic or wood cabinet, right? But there is a chassis, a metal chassis, and the radio circuit is inside there. Now, because in the days when these things were produced with vacuum tubes, they just had a simple 2-conductor power cord, and it was easy to put it in one way or the other into the outlet plug. And therefore, you could end up that instead of the hot going into there, you could have the hot coming along the neutral side, and therefore it would make the negative side, supposedly, or the return path of the power in the radio hot. That is carrying 120 volts there. And you don't want that. So just make sure, and with a resistance checker, that the power line you've got coming in here is the one that's going to fit into the right part of the socket. In fact, why not just take a little indelible pen and mark with a black spot the end of the plug or the side of the plug that has the hot line on it, and that'll make sure that you stick it in the right way when you go to set up your radio to work on it. Notice that in an AC/DC chassis, there's a neutral, which is the return path, and a chassis ground, power ground, and then there's a chassis ground that's separate from that. Let's give you an example of that. Can you turn on to the slide that shows the Crosley radio? Thank you. Okay, typical 5 tube AC/DC radio, and you'll notice that all the little symbols for grounds are here, and those are all connected to the neutral, we hope, so that's the return path for the power. Here, 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 all these little symbols here, but you'll notice there's a different symbol here and down here. Now those are the chassis grounds. So at that point, you don't have a floating ground, you have a chassis ground. And you'll also notice that here on the power input, there's a 1 meg resistor with a 0.1 cap in parallel with it. Up here, there's just a single cap, a very low value single cap. It's probably a mica, probably a ceramic that's connected to the chassis ground. So those are the only 2 chassis grounds in this circuit. Let me ask you the question. Why are these there? Part of it. So these particular components here are to draw off any RF surges or transients from the power line to the chassis ground. The chassis acts as a final shield, and this guy up here is an RF ground. Because of the fact that you come along from your detector here, this is the diode, and you come along here, this is your AVC line, going along here, and then you come off, you take your audio takeoff on here. Before you switch it over to the audio, which starts to figure here broadly in terms of the volume control and the input to the grid, you have this small valued cap, I think it's 100 picofarads, something like that, and to a ground, to a chassis ground. And that's taking any kind of stray RF that's running along this line that might be left and decoupling it to the chassis ground. The chassis then acts as a kind of a metal shield for interference and RF frequencies that you want to get rid of. So that's why these values are chosen. This is a 1 meg resistor, so it's pretty high value, and a 0.1 cap, and that's to the power line interference and filter to take care of any RF transients and the power line come in, hopefully. Okay, now we're at this point here. All right, so assuming that we've got everything safety-wise set up, you then turn on the radio power, you turn on your radio, and you're running through the ISO, the isolation and variac combination at a low setting. Now here we get a little bit into what Radar was talking about in his presentation. If you slowly advance the variac from a low position to, you keep monitoring the current meter. Sure, there's no large current, and since with an AC/DC radio you're already connected up to all the rest of the tubes and the power inline or rectifier circuit, it's going to turn on slowly. But if you turn up the variac slowly, it also allows the electrolytic caps to reform after a fashion. Now you might want to do that because do you really want to replace all the capacitors in a radio every time just because it's an older radio? And particularly because electrolytics can be reformed. In fact, I was reading one article where, a vintage radio guy is talking about reforming electrolytics rather than just replacing them outright. And he said it was incredible that even some very, very old electrolytics could be reformed and turn out to be almost as good as new. Now, sure, with the paper caps and that, you might want to say, well, why fiddle around? I'll just replace those. We're coming up to another part, which is going to have to be another day, which will tell you how to deal with those and how to measure capacitances in general. But for now, try this out, and you might save yourself. Isn't it nasty pulling out those cans out of the chassis, and you have to get a great big 300 watt iron on them to pull out the grounding lugs on them and everything? Wouldn't it be nice if you could just kind of circumvent that and just reform them and allow them to stay in the radio? If you're doing it for yourself and you want to spare no expense, well, okay, but say you're fixing a radio for somebody else and you just want a good working radio that's reasonably reliable, why go to extra trouble? Okay, now, so just to finish off all of this, let's go on to transformer type radios. And this time you only need the variac. Of course, you don't need the isolation transformer in place because you already have a transformer in the radio. But you need the variac. And you go into point number 7 here. Pull all the tubes out of the sockets. Turn slowly, after turning on the power now. Advance the variac to ensure no large current draw or transformer heating. So this gets over to something that Radar also touched on. And the way to handle it is, now that you've got a variac with a current meter on it, you can actually determine up to the full VA or voltage amp requirement of the radio whether the transformer is working or not. If it's even at a low current draw, starting to heat up with no load on it, you know very well there's something wrong with the transformer. And without having to blow things up or fry things, you can find that out very readily by using this test. And finally, the last point, plug the tubes into the sockets down here. Plug the tubes into the sockets and advance the variac slowly to check for circuit shorts and allow capacitor reforming. Similar to what you did in the AC/DC radio, but now you've got the load in place, you've got the tubes all heating up, and you're checking the performance of the transformer under a load, under the typical load. You want to make sure that it might meet its specification in terms of volt amps, but does not exceed that. If it exceeds that, you know you're dealing with some kind of leakage or shorts in the circuit that was not intended to be there, and you're going to have to troubleshoot that. The reason why this test is important too, as mentioning to Greg, we were having a little discussion before the session, is that occasionally you're going to have transformer problems that only show up when the power is applied. And even at certain voltages, you can fire up a transformer, and this has happened to me, and it's full rated voltage, and it will break down occasionally. And it's called an intermittent dynamic short. And it's a real headache. Some transformers, of course, will short at a certain voltage anyway, and you have to know that, because you have to know whether you have to replace a very expensive item like a transformer or not. It might make the whole radio not even worth working on. So those are important tests, and that's the use of the power box. And we're over time for sure.